Okay, in this video we'll be discussing chem bonding, TBL questions, focusing on set A. Okay, so set A, question A1, the boiling point of H2O is greater than that of HF. Which statement correctly explains this? So for such a question, typically what will I do is to consider the structure. So as H2O has a simple molecular structure, right? Similarly for HF, simple molecular structure. So which means in this case, both compounds we are looking at IMF to determine the boiling point, melting point. So for H2O, we all know by now it has hydrogen bonding. Why so? Because H2O has a delta plus hydrogen that's covalently bonded to FO and N. Alright, and then the O itself also has lone pairs to do hydrogen bonding. Okay, HF similarly also has hydrogen bonding because H is directly bonded to a highly electronegative fluorine atom. So both have hydrogen bond. So the question is, which statements correctly explain why H2O has a higher boiling point compared to HF? So each hydrogen bond formed between water molecules is stronger than that formed between HF molecules. That is not correct. Why? Because what affects hydrogen bond strength is that the hydrogen bonds formed between HF molecules is actually stronger than hydrogen bonds formed between water molecules. Why? Because we look at the dipole moment. The dipole moment of HF bond is larger than that of OH bond because F is more electronegative than O. Which means, if we were to measure the dipole of the delta plus and delta minus, the delta plus and delta minus will be a greater difference. So as a result, the attraction between another HF molecule will be stronger because the delta minus is more delta minus, the delta plus is more delta plus in HF. So the larger dipole moment, the stronger the hydrogen bond. So option A is incorrect. Okay, there are more atoms in the water molecule than there are in HF molecule, so the permanent dipole is stronger in water. So if you look at this statement, yes, this statement, more atoms in the water molecule, that's correct. But if you look at more atoms, what does it affect? Does it affect PD? It doesn't, because when we look at atoms, electron cloud size, we are looking at it affecting ID, not PD. Alright? Next, there are on average more hydrogen bonds formed between water molecules than there are between HF molecules. This is a correct statement. Why is this correct? Because to consider, this is basically the concept of extensiveness of hydrogen bond. To consider this, we look at the limiting factor of the lone pairs versus the number of hydrogens. So in this case, for your water, it has 2 delta plus hydrogen bonded to O. Okay, we also have 2 lone pairs on O atom. So as a result, for both of them, we can therefore form 2 hydrogen bonds per H2O molecule. Comparatively, if you look at HF, we have only one delta plus H bonded to F. But we have 3 lone pair of electrons on F atom. So as a result, if I look at this, which is the limiting factor, I'm limited by the number of hydrogens I can hydrogen bond. And that's what I can form 1 hydrogen bond per HF molecule. Okay, and as a result, water forms more extensive hydrogen bonds compared to HF. Therefore, it has a higher boiling point. Now, in regards to part D, the water molecule has a greater dipole moment than HF. That's not correct. So dipole moment of HF is actually in fact bigger than that of HO bond because F is more electronegative than O. So the difference in electronegativity between H and F is larger. Alright, so this will result in a greater dipole moment. Okay, so therefore with this consideration, answer is C. Okay, moving on, we look at A2. Which of the following pair of liquids when mixed will give out heat? So basically, if you look at this is slightly a solid solvent kind of question to see whether 2 solutions when we mix, can it mix well? If it can mix well, it can then release heat. Okay, so quick recap of concepts. So imagine if I put my first species in this MCQ choice as my solute, the second species to be my solvent, basically the solid-solvent interactions will be the interaction between both of them. Okay, it's arbitrary which is a solid, which is solvent, it doesn't really matter. So all we need to do is now systematically look at the type of IMF present in each of these solid and solvent, and what's the IMF formed between the solid and solvent. If the solid and solvent can release more energy, because solid-solvent interactions, it's a bond-forming process, it's exothermic, and then this energy release is more than the energy required, you do expect heat to be given out. Okay, so now with one look at this, we look at whether each molecule contains what type of IMF. Again, all the compounds here are simple molecular. Alright, so we're looking at what kind of IMF they form. So CHCl3 is a polar molecule, so you have PDPD. C5H12, because there's no electronegative element, only carbon and hydrogen, it's going to be non-polar, you only have IDID. Now, between a non-polar molecule and a polar molecule, what type of interaction can form? Only your IDID. Okay, so non-polar and non-polar can only form IDID because a non-polar cannot form any other things. Right, so if comparatively you have IDID versus IDID and PDPD, which is stronger? Of course, the PDPD will be stronger than the IDID. So, energy required in solid-solvent to break solid-solid interaction and solvent-solvent interaction is higher than that of the energy released during solid-solvent interaction. Heat is absorbed. Alright, so A is not the correct option. What about B then? B, you have CCl4. CCl4 is non-polar. Why? Although it has a polar CCl bond, but it's tetrahedral in shape, the dipole moment cancels out. So it's non-polar, it only has IDID. In this case, your propanone, C double bond O, it's polar, and there's no other polar bond, so you do have a net dipole is polar, you have PDPD. So again, you have a non-polar and a polar substance. The type of interaction you can form only, it's IDID. So again, very similar to the earlier example, the heat required or energy required to overcome solid-solid interaction and solvent-solvent interaction is not sufficient, alright, to be provided by the energy released during solid-solvent interaction. So heat is being absorbed. Okay, for part C, we have again CCl4, non-polar, IDID. But for this, because of the OH bond, you have a delta plus H and O, you do have hydrogen bonding. Alright, so again, you have a non-polar and hydrogen bonds. The type of interaction will only be IDID. So similarly, can IDID be stronger than hydrogen bonds? Cannot, and therefore, you need more energy to overcome solid-solid interaction and solvent-solvent interaction than the energy released during solid-solvent interaction. Heat will be absorbed. Which brings us to the last point over here. The last point over here, CH2Cl2, it's a polar molecule because you only have two CCl bonds that are polar. This molecule here, because of the CO bond, is polar. So you have polar, PDPD, CH2Cl2, and your propanone, both are polar, they can also form PDPD interaction. So in this case, you have PDPD for your solid-solvent, solid-solute, and solvent-solvent interaction. And this is the only choice that allows for heat to be released because they are comparable in strength. So recall your explanation, energy released from the intermolecular PDPD between your solid-solvent interaction sufficient to overcome the intermolecular PDPD between your solid particles and your solvent particles. Alright, so this will allow for heat to be released, and therefore option D will be the correct option. Okay, moving on to A3. A3, we have AlH3 reacting with CH3,3N to give this compound. Which statement of this compound is correct? So, AlH3, if you draw it, okay, it's simple molecular. You have 3 bond pairs around aluminum, so it's a trigonal planar shape. But interestingly, you do note that the aluminum atom is actually electron deficient because it has only 3 bond pairs. Alright, so it has only 3 bond pairs, so it's electron deficient. On the other hand, CH3,3N, you do have a lone pair on the end. So how do you think these two will react to give this compound? So you can see over here, N is bonded to Al. So it's quite obvious that the N will dative bond to the Al to help the Al achieve its octet configuration. Okay, so over here there's a reason why I draw this in this particular manner. This N has 3 bond pairs, 1 lone pair. So the shape will be trigonal pyramidal, 107 degrees. So the Al origin was trigonal planar, but after accepting a lone pair of electrons from N via dative bond to achieve octet configuration, you get a structure that looks something like this. So you can clearly see that the dative bond is formed between the N and the Al. But now, once you form the adduct with the dative bond form, both N and Al has 4 bond pairs, 0 lone pairs. Right, 4 bond pairs, 0 lone pairs. And as a result, both N and Al will become tetrahedral in shape. Alright? So let's take a look at the option. The Al atom is electron deficient. Is the Al atom over here still electron deficient? Not true, because if you take a look at this Al, I've highlighted in orange here, this Al now has 4 bond pairs, it has 8 electrons, it's no longer electron deficient. Yes, previously it was electron deficient, but now it's no longer after the compound, the adduct is formed. Is it dimeric? So it's not dimeric. Why? The word dimeric means 2 repeating monomers. So there's no repeating units unlike your Al2Cl6. Okay? The bonds around the Al atoms are tetrahedrally arranged. You can see clearly they are tetrahedrally arranged. So 4 bond pairs, 0 lone pairs. Therefore, shape around the Al atom is tetrahedral. And last but not least, is bonded. Is it bonded via PD-PD, permanent dipole attractions? That's incorrect, because it's actually through a dative bond. So therefore, of the option, only option C is correct. Okay, and that's your A3. Okay, moving on to A4. For ion, IF4Z minus, it has a square planar structure. By considering the shape, use the value of Z. So for square planar structure, you must have 4 bond pairs, 2 lone pairs. Okay, this is basically from the VSEPR concept. Alright, square planar, 4 bond pairs, 2 lone pairs. I, as a central atom, must have 2 lone pairs. Okay, so I just draw a square planar outline first. So iodine, we know that it has 7 valence electrons. How do I know that? Because iodine is in group 17. So you have a dot, dot, dot. That's the maximum amount of electrons I can contribute. So which means with the fluorine, it can only form 3 single bonds with fluorine. Right? Because it has only 3 additional electrons. Because why? The 4 electrons were used as the lone pairs. Alright? So, which means this last fluorine can only be bonded to iodine through a dative bond. Right? Because if not, it can't remain bonded. So, recall again, I say again, if you look at the number of dots around iodine has only 7 valence electrons. I've highlighted in yellow and orange. Alright, so which means one of fluorine must have gained 1 electron to form a dative bond. So therefore the charge will be minus 1. Right? Why? Because only gain 1 electron. Okay? So explanation as explained. So iodine, 7 valence electrons, 4 of these must be involved as lone pairs. 3 valence electrons available for bonding, so can only form 3 single covalent bonds. So 1 IF bond must be formed by a dative bond, meaning that the 1 fluorine atom must have gained 1 additional electron. Okay, moving on to the last question. A5, which statements of Al is correct? So Al is a giant metallic lattice structure. Okay, so it has high melting point due to your strong metallic bonds. What's your metallic bonds? It's a strong attraction between delocalized electrons and your cations. So statement 1 is correct. Will Al have stronger metallic bonds than sodium? Yes, that's correct, because what is the strength of metallic bonds related to? Okay, there are 2 factors that affect strength of metallic bonds. Number 1 is the number of valence electrons per atom. So Al has 3, and A has only 1. So you have stronger bonding. Second thing is we look at the charge density of your metal cation. So Al3 plus also has a higher charge density than sodium. Okay, so statement 2 is also correct. Now statement 3, it has high electrical conductivity due to ability of its ions to carry the current. Is that correct? So do metal carry current due to ions. That's incorrect. This should be the delocalized electron. So statement 3 is incorrect because of the word ion. It should be changed to delocalized electron. Therefore, only 1 and 2 is correct. Answer will be B. Okay, so let me just erase the answers. If you prefer a more detailed explanation, it's over here. Okay, with that, we are done with TBL Set A.